In this lecture, we will be learning about quadratic forms. Quadratic forms are an important topic in linear algebra, but they usually don't come up in a first course in linear algebra. First, we'll give a definition. Given a matrix A, square matrix, so an n by n matrix of real entries, the quadratic form associated with A is defined as, and sometimes we'll write it Q sub A of X, and it's X transpose AX. For X, a vector in Rn. If we take a look at the dimensions here, and we consider any vector X a column vector, then X transpose is 1 by n, A is n by n, and X is n by 1. And thus, this product is 1 by 1. Or a scalar. And really, what this is a general quadratic expression in the entries of X, where the matrix A gives you the coefficients. And so the way you can think of this is every pair xi times xj for I and j in the set 1 to n appears in that quadratic form X transpose AX. More specifically, this quadratic form X transpose AX can be written as the double sum I equals 1 to n, sum j equals 1 to n of aij xi xj. So again, every pairing of xi and xj appears here, and each such pairing has coefficient aij. And so in this way, this is a quadratic expression in the entries of X. Let's look at an example to make this a little bit more concrete, and let's just look at what happens in the case when n is equal to 3. In this case, X transpose AX would look something like this. We'd have our X transpose, and then our A is this 3 by 3. And so we have A11, A12, A13, and then A21, A22, A23, and finally A31, A32, A33 times X. And we'll write X as a vector here in terms of its components, x1, x2, x3. We know by associativity of matrix multiplication that we could either do this product, the matrix and the vector X first, or the product X transpose A first. And we've set this up to do the A times X first. And so this expression becomes X transpose, which now we will write as the row vector, x1, x2, x3, and let's write out what that AX term looks like. Recall our rules for matrix multiplication. This matrix here is a 3 by 3, this vector is a 3 by 1, and so the result is a 3 by 1. We use the outer dimensions of this product. And the way we get these three entries of this new vector, this new 3 by 1, for the first entry, we take the first row of A and we take its dot product with this vector. And so when we multiply the first entries, we get A11x1. To that we add the product of the second entries, A12x2, and to that we add the product of the third entries, A13x3. And so again, you can see we're doing a dot product of this vector and this vector. For the second entry, we take the dot product of the second row of A and this vector x, and that gives us A21 x1 plus A22 x2 plus A23 x3, and finally we take the dot product of the third row with this column vector x, and we get A31 x1 plus A32 x2 plus A33 x3. We now note that we have a 1 by 3 matrix here, and here we have a 3 by 1. Even though each of these long lines is kind of long, each entry is just a scalar. And so this second term is just a vector with 3 entries. And so a 1 by 3 multiplied by a 3 by 1 is a 1 by 1. And this is actually just a dot product. So we're taking a dot product of this row vector and this column vector. So the first entry in that dot product will be the first entry of this vector here times the first entry of this vector, which is this expression in the top. And so we get x1 times that A11 x1 plus A12 x2 plus A13 x3. To get the second entry, we take the dot product of this second term x2 and the second term here. And so this will be plus x2 A21 x1 plus A22 x2 plus A23 x3, and finally we take the product of x3 and this third term, and so we have plus x3 times A31 x1 plus A32 x2 plus A33 x3. And we now notice that every possible pairing of xi and xj appears here. Here, this term here, we have x11. Here, we would have x1, x2. For this term, we would have x1, x3. Here we have x2, x1. And notice that we have that actually showing up twice. Here we have an A12, x1, x2. Here we have an A21, x2, x1. But because of commutativity of multiplication, x2 times x1 is the same as x1 times x2. So we actually care about the order of the pairings. You can think of it as this gives you the x1 times x2 term, and this gives you the x2 times x1 term. But as we go through this here, we see that every possible such pairing appears. And so this expression can be written as the sum I ranges from 1 to 3, sum j ranges from 1 to 3, of aij, xi, xj. And so you see in this kind of quadratic form, it's the coefficients of this matrix A that show up in each pairing, xi times xj. And this turns out to be extremely handy in application. In particular, two applications where it very commonly comes up in are nonlinear optimization and when you're dealing with covariance or correlation matrices. These quadratic forms come up quite naturally and frequently. But this is a very common tool in linear algebra, and you'll see this used quite a lot.